Hi guys, welcome to Chemistry Vodcast 1.2. We're going to talk about significant figures today. And this comes about because of a problem like this. We punch in a number like this in the calculator, 26 divided by 3.4. We get this giant, huge number at the end, and you know you're not supposed to write that in the answer blank. So we're going to talk about how do we get there, why we would not want a number like that, and what we do want it instead. And that's what sig figs is all about. Sig figs starts out with the idea of precision. Our instruments of measurement, the things that we use to take measurements, have a certain amount of precision. If we had a ruler like this, say that was marked in just centimeters, only had marks for centimeters, not very precise. If we were going to make a measurement, we'd have to say, well, it's almost 3. Maybe we can make a guess that it's about 2.5 or 2.6. We're sort of estimating that last decimal. If we had a slightly different instrument, something that's just a little bit more precise, like this ruler where we've got half hash marks, so each half centimeter, we could make our measurement a little bit more precise. So for instance, in this case, I definitely know that it's at least 2.5, and it's a little bit over that, so I would say that making a measurement of 2.6 or maybe 2.58, where we estimate that last amount, 2.60, that last digit there, that's going to be what we call the uncertain digit. That's the one that you have to estimate at the end. You do that in all measurements. And so just another few examples of doing measurements here. We're measuring liquids, another way we would measure. So in a beaker, if we look at this first one, the hash marks are at about every 10 milliliters. I'm above 40. I'm close to the next hash, which would be 50, so about 47. And again, that 7 is the uncertain digit. Over the graduated cylinder, I'm definitely above 36, maybe about halfway between, so maybe 36.5. Again, that 0.5 is uncertain. And then on a burette, we're reading this, and so we're at 20 point, I'm over 3, I'm close to 4, so 20.38. So again, that uncertain digit, but obviously you can see that burette, a lot more precise. Okay. We're down to the hundredths place, and so that's a lot more precise there. So how do we know then, if we have a number, how many of those numbers that we just talked about in a measurement are significant? So here are the rules. You've got the rules in your notes, but we're going to go over examples of each of these rules as well. So rule number 1, pretty simple, non-zeros are significant. Okay, and since that makes up 90% of your numbers, that's pretty good. So if we look at something like 63 grams, both of those digits are non-zero. 6 is non-zero, 3 is non-zero. They're two significant figures. The second rule is exact counts are always significant. In fact, they're infinite. Okay, and what's important about that is that that's not actually a measurement. Okay, that is a count. Counts are different than measurements. So anytime you have an exact count where you've counted something specifically, that has an infinite number of significant figures. In other words, an infinite precision. Next part of the rule there, and I think I've got a little jump in my slide here, so just bear with me. Okay, so rule 3, zeros may or may not be significant. Leading zeros are never significant. So if you look at this number, 0.074 meters, what we mean by leading zeros are zeros in the front of the number. It doesn't really matter for a leading zero where they are in relation to the decimal. If they're at the front, they're not significant, so we don't count them. Okay, as far as the significance, and we'll see where this goes to the calculators here in a minute. So we count the non-zeros, the 7 and the 4. Those are significant. Okay, so that means we have 2 sig figs in this particular problem. So 0.074 has 2 sig figs. The next part of that rule, where we're trying to figure out zeros may or may not be, so leading zero is easy, never count. The next rule is pretty easy too. If it's a captive zero, it's always significant. And what we mean by captive is that it's a zero in between numbers that we know are significant. So in particular, in between non-zeros, this 0 in 804 kilometers is in between an 8 and a 4, which are automatically significant, and so that makes the captive zero, the one in the middle, also significant. So we count them all up, and that's 3 sig figs. Okay, so those are pretty easy. That's the stuff about sig figs that's easy. This next page here, this next slide here, gets a little bit harder. This is where it gets a little bit harder to figure out, a little bit harder to discern what's going on. So let's talk about these rules. Trailing zeros, that would mean zeros at the end of a number. Okay, leading zeros at the beginning, trailing at the end of a number. They're significant in a couple of cases, and you'll see that there are three things here. That's the case where they are significant. Okay, so rule number one: if a number ends in a zero and there's a decimal given, okay, then it's significant. So if you look at this 120, the decimal was already written there, not assumed, it's already given. Okay, that means that that zero is significant. Okay, that zero is there for precision. That tells me that my measurement is precise to the ones place, not just the tens place. Okay, so that means we got 3 sig figs in this particular case. Okay, so that one's a little hard to find, but if the decimal is there, I mean, it's there for a reason. If it's specifically given at the end of the number, it's there for a reason. So if we're talking about zeros to the right of a decimal, okay, so in this case, we got 404.00. If they're to the right of the decimal, they're there to show the precision of the measurement. Okay, and that means they are significant. Okay, we know that the zero in between the fours is significant. It's captive. But the 2 zeros at the end of the number to the right of the decimal, trailing zeros to the right of the decimal, are significant. Okay, and you see that coming up there too, at the end of the number. If they're to the right of the decimal at the end of the number, they are significant. So that means in this case, the 4 and the 4 are significant, the 0 in the middle is significant, and the 2 zeros at the end are also significant. So that means 5 total significant figures. Okay, now the last case, and this is the one that starts to trick people up, this is the one that makes it really hard to do rounding and stuff like that. If you look at a number like 7,600 meters here, they're not significant. Okay, they would be significant if we went back to rule 1 there and there was a decimal given. But if the decimal isn't explicitly stated, those zeros are not significant. Okay, so the only thing that's significant in this case is the 7 and the 6. So we got 2 sig figs in that number. Okay, so we're going to run through a few examples here just to make sure that you sort of know what's going on. I'll try to explain these as best I can. Depends on how fast I did them. So everything in number 1, it's all non-zeros, so 3 sig figs. Number 2, those are leading zeros. Cancel them out, they don't matter. So that's 2 sig figs. Number 3, got a captive 0. Okay, so 1, 2, 3, 3 sig figs. Number 4, we've got trailing zeros. Okay, they're at the end, and there's no decimal given, so they don't matter. So we cross those out. The non-zeros are all that matter. We got 2 sig figs. Number 5, leading zeros, again, cross them out. The captive 0 in between the 2's counts, so that's 3. Go up to number 6, there's a decimal given, explicitly stated, so that means that 0 is significant. Okay, so that's 3 sig figs. Number 7, they're trailing zeros after the decimal, to the right of the decimal, they count. That makes that other 0 captive, so all 5 of those are significant. Number 8, cross out the leadings, captive counts, trailing it to the right of the decimal also counts, so that's 5. Number 9, 28 pencils, that's a count, always infinite. Okay, so it's not a measurement, it's actually a count. Anytime it's a count, it's always infinite. That's an easy one, that's always a gimme. Number 10, we're going to see that's a special case, it's a conversion factor, it's infinite also. Because that is an exact equality there, and that, by the way, is stated wrong. It's not 1,000 meters equals 1 meter, it's 1,000 meters equals 1 kilometer. So what does this have to do with calculations? How does this work out? Because this is where it really matters for us in chemistry. So there are a couple of different ways to do calculations. The first one I'll show you is addition and subtraction. They use the same set of rules. So we're going to add two numbers here, 14.35 grams to 2.7 grams. We punch that into our calculator and we get 17.05 grams. Now, what this shows is that my answer is more precise than one of my measurements, and that's why we do sig figs. That can't count. So what counts in addition and subtraction? The least number of digits after the decimal, that's what you round to. So the 2.7 only has one number after the decimal, so my answer should only have one number after the decimal, so 17.1 grams. Okay, now, let's go back to this thing we had on the calculator at the beginning of the video. Big honking number, that's what we're going to work for the next problem, for multiplication and division. They both work the same way. This is what you'll see the most of, and they're actually a little easier than addition and subtraction. So we take that 26.0, okay, we're going to divide that by 3.4. This is what we did at the very beginning of the video. Okay, and don't worry about the units right now. Units do matter in chemistry, but we'll talk more about that in the upcoming segment. So punch that in your calculator. you get this enormous number, a number that you know instinctively you should not put all of that down on the paper, and if you do, it's going to be wrong. But you kind of know that anyway. So we got 7.647058824 grams per mole. That's just the units. I don't want to put all that down. Where do I round that then? So the rule for multiplication and division is it's the least number of sig figs of any of your measurements. So the first one has 3, right? Okay, it's got a 0 after the decimal. Second one has 2. There's no zeros there, so we just count them and there's 2. So what we do then for multiplication division, this is most of what we do, is we round to the least number of sig figs. In this case, 2. One of our measurements had 3. One of our measurements had 2. We're going to round to 2. Okay, so we underline that in our original answer, 7.6. Since that's a 4 after the 6, we don't round up, so it just becomes 7.6 grams per mole, and that's exactly where we want it.